my writing?
Yes, Professor.
Okay. So we said that when the data is finite, that means typically n is less than 30. Um, we talk about finite data set, and we use t distribution to analyze finite data set. And here we said that if you have n number of data and we want to know the interval within which some P% of data is going to lie, then we can find that out as this. So use xi with x mean plus minus p degree of freedom probability sx, where p is expressed in terms of percentage. So if you have a t distribution curve and we want to say that um, where is the interval that contains p% of data. So that is this area under this curve. So that interval is going to be basically minus p mu p sx p plus p mu p s. Okay. So if you want to know what is the probability that a data will fall in the range, then you would have PSX known and you find probability, or vice versa. If you know what is the limit, knowing the probability, or what is the probability knowing the limit, you can accordingly find out. We said that the t variable that we defined as t is x bar, which is the mean of a sample, minus the true mean divided by sx divided by square root of n. So then we said that this is only from a single data set, but if you have m number of data sets, m different data sets, and each data set will have n measurements, then we said that we can talk about the standard deviation of the population, the mean, standard deviation of the mean, which can be found as Sx divided by square root of n. All right. So this is the standard deviation of a single data set, standard deviation of a single data set, and this is the number of measurements in a data set, and this is basically the standard deviation of the means of each of these data sets. Okay, so basically now instead of using Sx, a better estimate of the population mean can be so you can write a better estimate of the population mean is that you take a finite data set and find out its mean, then you do plus minus t mu p sx mean, or which is equal to x mean p mu p sx divided by square root of n. So what it means that you take a single data set and you find out its mean, you find out its standard deviation, and divide that with the square root of the number of data points. And if you want to know what is the probability that the population mean will lie within that interval, so depending on so mu is basically n minus 1, p is that probability. So you can estimate the population mean. Okay, so we will take an example and through which you try to understand this.
Professor, I
Yeah,
just had one query.
yeah,
Yesterday, you drove, you like drawn too many of this shape that you have drawn over here, right?
yes, yes,
So basically, that means that the peak of that, like what I mean to say, mean of that, if I join locus of all those this thing, then it
yeah,
will fall in the same shape that you have drawn over here, right?
yeah, yeah.
Am I right in like
So
saying
what
that?
I was meaning there is basically visual data sets, each of these m different data sets here. Okay, so you will have basically x mean of the first one, x mean of the second one, and similarly the x mean of the mth one. So what it say is that these means will also follow a standard deviation, so normal distribution curve. So that means each of these points will be basically the means. Okay,
Right, sir. Right, sir. Thank you.
and then that will predict this population mean accurately. That is exactly what it is saying. Okay, so we take this example. So the data set that we will be referring to is what I had written in the previous class. Let me show that to you because I don't want to write that again. I think I will have it here. Let me just. I think in one of the examples I had written out 20 data points, right? So let me find. So this data that I am going to refer to is this data on your screen. Are you able to see this data point?
Yes, sir. Yes, sir.
20 data points. So I have already shown this to you. So this is the data that I will be talking about. So here I would like to find for that data set the sample statistics. That means we are interested to know the sample mean and sample standard deviation. Then we want to estimate the interval values over which 95% of the measurements of X should be expected to lie. And we also want to estimate the true mean at 95% probability based on this finite data set. Okay, so I will tell you what we are interested in. So we have this data set. So we are interested to find the mean value, the standard deviation value, That is the point number A. Point number B is that we want to estimate an interval of the value of X, okay, within which 95% of the measurements of X should be expected to lie. So we are going to define that interval within which 95% measurements are going to lie. And number 3 is that we want to estimate the true mean value of X at 95% probability. Okay. So how do we do this? So first we find the mean. So we find mean, which is 1 over n sum xi I equal to 1 to n. So if I take all these 20 values, add them up, right, and divide by 20, then I would get 1.02. Okay, so you can do that, check that for yourself, and I can estimate the standard deviation for this finite data set, which is 1 over n minus 1, that is the degree of freedom, sum I equal to 1 to n, xi minus x mean that we have just evaluated, square of that, and whole square root. So if you take each one of these 20 data points and subtract the mean value, which is calculated here, and square them and add them up and divide by this n minus 1. N minus 1 is basically the degree of freedom, which is 19. 20 minus 1 is 19. So then if we calculate, this will come out to be 0.16. Okay, so we have found the sample statistics. Now we want to estimate the interval of values over which 95% of measurement of X should be expected to lie. So essentially, we want to know what is T nu P, and in this particular case, nu is 19, and 95% of the measurements, so we take the probability to be 90.95 because that is the area under the curve. So that we can read from the table. Okay, so I will show you the T table. I think I have not shown you that. So the T distribution table are you able to see this table that is on my screen?
Yes.
Yeah.
Yes, sir.
Yes, sir. Yes, sir.
If you look at this table, it has the degree of freedom in different rows. So you have 1, 2, 3, etc. up to infinity. Okay. And in different columns, you have the probability. Okay. The subscript here stands for the probability. So 50%, 90%, 95%, 99%. Okay. And you can see that when degree of freedom becomes very large, these values that you get here correspond to the values for the normal distribution, because that is what we last class we discussed, right? When the data number of data points becomes very large, your T distribution would approach the normal distribution. Okay, so I will show you, for example, when nu is infinity and you talk about, let's say, 95% probability, the value of T is 1.96, right? So now, if we look at the Z distribution table, so if you say corresponding to 1.96, okay. So what is the probability value? it is 0.475, but it is one-sided. Okay, so you have to multiply by 2, so that becomes 95%. Okay, so essentially corresponding to this probability, the value of Z is 1.96, which you see in the T distribution table. So essentially, the point that we are trying to make is that when number of data points becomes very large, T distribution becomes the Z distribution. For example, you say 90% probability, you see 1.645. Okay, 1.645. So if you go to Z distribution table, so 1.64. Okay, so you see that it will be between this and that because 645. So you can see that if you interpolate, you will get exact of that will give you 90% probability, right? So that is what I wanted to tell. But in this particular question that we are trying to solve, the new is 19. So you go here, that is 19. And then we say that 95% of the data, so that means you go to 95% here, so that is 2.093. So this is the value of T. Okay, this is the value of T. Unlike Z distribution, where the different rows are the value of Z, and you find the probability. Okay, but in T distribution table, you have the number of, the degree of freedom, which is n-1, and corresponding to the probability, you read the value of T. I mean, you can also do the reverse, but it is the way it is tabulated. Okay. So for this particular case, we say the value of T is 2.093. So we note down here that is 2.093. So I can now find the interval. Okay, so the interval is going to be, so xi value will be 1.02. That is, so by definition, what it was x mean plus minus p mu p sx. So this is 1.02 plus minus t is basically 2.093 into sx is 0.16. So that is 1.02 plus minus 0.33. Okay. So this is the interval within which 95% of the measurements would lie. So you can do the same for if you want to know 99% of measured data, then you have to read, your probability becomes 0.99, or 50% data, your probability becomes 50.5. Okay. So now the next is we want to estimate the true mean value of x at 95% probability based on this finite data set. Okay. So how do we do that? We first find out your formula is n plus minus sx divided by square root of n. Okay, and this is basically your sx bar, right? So you find sx bar, which is sx square root of n is equal to 0.16 divided by square root of 20, and this will be basically 0.036. Okay, so then your population mean becomes plus minus. Oh, I have missed out t. That is important. So here we have t mu p. So t mu p into 6 bar. You have 1.02 and this is already we know is 19, and this is 0.95. So the value is 2.093 into 0.036. That will be 1.02 plus minus 0.08. So basically it says that if you have the data, right, and this is 1.02 and you have 0.08 minus 0.08. So basically, not really, this would be 1.02 minus this, and this would be 0.02. So it says that within this interval, your x prime, the true mean would lie, and that probability is basically 95%. Okay, so the true mean is somewhere in between. Okay, and that probability is 95%. Right. So now, if you have only, we said that when we talked about this Sx bar, we said that you can have m different data sets and each data set containing n measurement, but we do not really constitute m different data set. We only have one data set and n measurements. From there, we predict what is the true mean. But in some scenario, let's say you have really m different data sets. Okay, let's say, I mean, you are interested to measure temperature of a surface, and let's say on the first day, one of you measured the temperature and you got some, 20 data points. Next day, let's say, again you measure, or somebody else measured, and you have again some 20 data sets or 15 data sets. And then next day again somebody else measures. So you basically have 3 different data sets, each having some 15, 20, 18 data points. So in that case, when you want to really find out the mean or the standard deviation, you use what is called pooled statistics. Okay, so we talk about pooled statistics. Yeah, pooled statistics, you have basically m replicates of measurements, and each replicate contains n data points. Okay. So you basically have I, let's say, going from 1 to up to n, and your j goes from 1 to up to m. So you really talk about the data points now no longer is xi, but ij, right? So the first stands for the data number, second stands for the data set or the replicate. Then you talk about pooled mean of x. So you find the pooled mean of x. Okay. So you write this using a different symbol, and you find this as 1 over mn, j equal to 1 to m, I equal to 1 to n xij. Okay. And you can also talk about pooled standard deviation of x. So you write Sx as 1 over m into n minus 1 j equal to 1 to m I equal to 1 to n xij minus xj mean. For each data set, you will have a mean square whole square root. Okay. And here the degree of freedom, you notice that has become, so this is basically your mu, which is m to n minus 1. And similarly, the pooled standard deviation of the mean Sx is basically Sx divided by square root of m into n. So if you know the pooled mean, yeah. If you know the pooled mean, yeah.
How do we, attribute the degree of freedoms as m into n minus 1? Any reason for it?
So basically, for each j, you are finding the mean, right? I think we discussed why you use n minus 1. That is clear, right?
N minus 1 is clear, yeah.
Yeah. So here, basically, they multiply with m because m is like m different data sets, and so they are independent of each other. So you do not really bring in m minus 1 because you calculate the mean only for a particular data set. So the degree of freedom, basically, the one stands for the mean of a particular data set. Okay. And since you are using for m data sets, so you are dividing with m.
Got it, sir. Got it. Yeah.
Sir, what is the significance of this pooled statistics? Because we are already taking the sample from the population.
Yeah. So I am telling you that here in this example, I mean, you have only one particular data set. You have 20 data points, and you are doing this analysis. Okay. When you have, let's say, 3 different replicates and each having, let's say, 20 data sets, if you want to do this kind of analysis, you have to use pooled statistics to find the pooled mean, pooled standard deviation of the means. And then these values you can use, I mean, in the analysis that you did in the previous example. Okay. So there is a difference between the two. I mean, these data sets are not, these data points are not coming from only one data set. So they are different data sets. When you have different data sets, this is the way to handle it. That's all it is telling you.
So can we say that, suppose we have got to know the pooled statistics, like pooled standard deviation and pooled mean and everything.
Yeah.
But can we use this as a hypothesis to understand, to reject or to accept the earlier calculations?
So the acceptance and rejection of data, I think we will talk about soon. I mean, maybe in the next of the class after that. There is a criterion called Chauvenet's criterion. Which data we accept, which data we reject. So that is something that is coming. But here we are not talking about acceptance rejection. If you want to talk about data acceptance, data rejection, you have to use Chauvenet criterion. We have not gone that far. But here you are saying that all the data points are acceptable according to your Chauvenet's criterion. So but these are not coming from a single data set. There are multiple data sets. So when you have multiple data sets, so you have to use pool statistics. Okay.
Okay, Professor. Yeah, thank you.
So now the question is, what if the number of data points in different data sets are not the same? Okay. So how do you find the pool mean and pool standard deviation? Because I is not the same for different value of j. So there you basically do a weighted mean and weighted pool standard deviation, and same for the standard deviation of the mean. So I will just quickly write down those formula as well. So if you want to find out the weighted mean, when number of needs set are different, so basically there you find j equal to 1 to m nj xj divided by sum nj. Okay, so j stands for a particular data set. So for a particular data set, you find what is xj, then you write that data set number and the number of those data sets. Okay, and similarly, the pool standard deviation Sx you can find as mu1 Sx1 square, because the degree of freedoms are going to be different, right? Because n is different between that different data sets. So you are basically going up to mu m Sxm square below you have mu1 plus mu2 up to mu m. Okay, so that means for individual j equal to 1, j equal to 2, up to j equal to m, you have to find all these Sx2, Sxm, and then you use this to find the weighted mean, weighted pool standard deviation, and then the weighted standard deviation of the mean. That is basically
Sir, the square root involves only the numerator or the denominator also?
both numerator and denominator. Okay, so this is when for each j your n is different. Okay, so this is n1, n2, then you have to do this. Right. So, and then once you calculate these variables, rest of the analysis is similar to what we have discussed. The t distribution theory applies to these multiple data sets in the same way. Okay, just the calculation of these statistical quantities is going to be different. Right. So I wanted to talk about little bit about the design stage uncertainty analysis. Actually, I should have talked about this before talking about uncertainty from the data. So let us first try to understand uncertainty. When you do experiment, it is very important to know what is the uncertainty in your measurement, right? Typically, we say that the measurement, the measured data would involve some error. Okay, but error is a qualitative term. Okay, because error is, as we discussed, is the true value minus the measured value. So that is, true value is not known. So error is basically a qualitative term. But if you really want to know how accurate is your data, you have to talk about uncertainty. Okay, so error is basically can involve the different inputs to the measurement that can affect your data. Okay, so but the consequence on the measurement data is represented in terms of uncertainty. Okay, so uncertainty is a property of the result, property of the result, whereas uncertainty, whereas error can be the property of the instrument. We talked about various kinds of errors, right? Linearity error, hysteresis error, many different kinds of errors that we discussed. So errors are basically properties of instruments, but uncertainty is the property of the result. Okay. Now, when we talk about picking some instrument for certain kind of measurement, let's say we pick one.
Question, sir.
Yeah.
Purely from a mathematical point, can we consider it like an inverse of probability, because it's uncertain, so it's in the probability of it not occurring or something like that?
No, I mean okay. I mean you are thinking in that direction, but really the objective of your experiment is to find the true value, and what you find is in the mean value, and then you specify this uncertainty. We wrote, right, T nu P Sx over square root of n. So this is basically the uncertainty. Okay, and when uncertainty is there, of course you have to specify with some probability. Okay, so
Okay.
their probability comes in that context. You got it, right? So this is uncertainty. We are using the symbol UX. Now this data analysis that we went through, right, for a finite data set, this is basically your uncertainty in the data, because this is the true value. This is what you measure. So you say that my measurement involves error, but error is always qualitative. Okay, it can involve property of the instrument, it can involve property of the measurement. That means how it is influenced, what all things are affecting the measurement. But if you want to quantify, you have to talk about uncertainty. Okay, so uncertainty actually puts a number on how accurate your data is. Okay, so this is coming from the measurement. Okay, so uncertainty, when you talk about uncertainty, there are two things that we talk about. First is design stage uncertainty, and then uncertainty of data. So what we have been discussing is basically the uncertainty in the measured data. Design stage uncertainty becomes important when you want to select an instrument for certain measurement. Okay, let's say you are trying to measure the length of a structure or length of a bar down to something like 0.001 millimeter, right? So if you use a typical scale, that these school kids use, right? So the minimum that you can measure is within a millimeter, right? So you cannot really go to 0.001 millimeter. So in that context, the design stage uncertainty analysis becomes very important. Okay, design stage uncertainty, to calculate the design stage uncertainty, there are two things that are important. One is the resolution of the instrument, and the second is the different kinds of errors that instrument would carry. Right? So the design stage uncertainty have the zero order uncertainty that talks about the resolution of the instrument, and then errors in the associated with the instrument. Errors associated with the instrument. So both can affect the design stage uncertainty. First, let us talk about the zero order uncertainty. The zero order uncertainty is typically U0, that is the zero order uncertainty, typically is taken as half of the resolution. Okay, let's say you have a scale, so you have having 0.2, 0.3. Now, if you measure length of a structure, and the structure is basically lying somewhere in between, somewhere here or here. So if you want to know, what is the zero order uncertainty of this instrument, or how it will affect your measurement, the zero order uncertainty will be basically half of the resolution. So here resolution is 0.1, so zero order uncertainty should be 0.05. Okay, and this can be written as plus minus, because it can be either on this side or that side of the center line. And typically in statistics, this definition of zero order uncertainty has a by default probability of 95%. Okay. Now, if you have some different kinds of errors that we talked about, right, introduction. So if you want to find the total uncertainty due to the elemental error, total uncertainty due to the elemental error, that means the errors associated with the instrument, then you can find that Ux is your U0 square plus U1 square plus U2 square up to UN square. So these are contributions coming from elemental error and this is coming from pseudo uncertainty. Okay, so I'll take an example where it will be clear. Let's say we have a force measuring instrument. And the resolution of the instrument is 0.25 Newton. The resolution is specified as 0.25 Newton. And when you bought this instrument, there is also a data sheet along with resolution. You have linearity error. Is 0.20 Newton over the range of operation. And hysteresis error is 0.30 Newton. Let's say is only 2 errors are specified. Now you want to find the design stage uncertainty. So you can find, we can rather specify as UD. So UD is U0 square plus U1 square up to U1 square. We only have U linearity, which is 0.20. We have U hysteresis, which is 0.30. Then U0 is half of the resolution, that is half of 0.25, that is 0.1. Okay, so we have all the errors now, all the uncertainties now. 0.125 square plus 0.20 square plus 0.20 square. Take square root, we get plus minus 0.38 Newton. So how this helps? You bought an instrument and you found out the design stage uncertainty. Let's say you are supposed to measure force within increment of 0.1 Newton, right? Where you want to measure force with an accuracy of 0.1 Newton. Then let's say the design stage uncertainty calculation tells you that it is 0.38 Newton. You straight away know that this instrument is no good for you. Okay. So design stage uncertainty analysis basically helps you in selection of instrument, selection of the right kind of instrument for measurement. Okay. It has no impact on the, of course, it will have impact on the results, but it is different from the uncertainty in the data. Okay, so that is coming from the systematic and random errors sources, whereas in design stage uncertainty, you just calculate to make sure that the instrument that you pick to do certain kind of measurement is good enough. It will serve your purpose or not. Okay, so let me see what is the.
Professor, do we need to link anywhere the tolerance we are going to measure?
So yeah, I mean, that is what I was talking about. Let's say if you want to measure using certain, you have a very tight tolerance, okay, and your instrument is not, the design state uncertainty is not really serving a purpose, it can help you, right? I mean, in deciding whether what kind of instrument you need. So,
okay,
in that perspective, this is important.
Sir, one thing just,
Yeah.
like you said that 0.38 Newton, sorry, whatever it is, Newton.
Yeah.
Since it is more than, so you have put a cross over there. I think I missed that point.
Yeah, I said that this if you have a requirement that you want to measure force to the level of 0.1 Newton, right?
Right, sir.
Then this instrument, this particular force measuring instrument is not good enough for you.
So because resolution is lesser than the error that we have,
Yes.
right, sir?
Yes.
Fine.
The resolution of your measurement is less than the design stage uncertainty that you have for this particular instrument. So I wanted to talk about the propagation of uncertainty. So maybe we will do that in the coming class, but I will just give you some perspective. Let's say you are trying to measure pressure drop across a pipe, right? Which depends on many parameters like the velocity inside the pipe, and the length of the pipe, the diameter of pipe, the friction factor, how rough or how smooth the pipe is, and so on. Now, let's say you want to estimate delta P by measuring all these, right? So you want to measure velocity, you want to measure length, you want to measure diameter. Now, how the uncertainty in each one of these measurements is going to affect the uncertainty of the estimated value of delta P, right? So we talked about, if you remember in the very first class, we talked about the primary quantity and derived quantity, right? A derived quantity can involve several primary quantities. These primary quantities can be directly measured using some instrument. So you will have n number of primary quantities, and each primary quantity from your measurement will have an uncertainty, right? The question is how the individual uncertainties in each of these primary quantities are going to affect the uncertainty in the derived quantity that you want to estimate from these measurements. So that is called propagation of uncertainty. And there is a mathematical formula that we would write down to estimate that. And then we have, and then we take an example to estimate the propagation of uncertainty. But I would, in the interest of time, I would do that in the next class. If you have any question, we can discuss.
Sir, one question, sir.
Yeah.
Maybe I'm wrong. I don't know, but this 0.38, whatever you have mentioned at the last note, like we
Yeah.
can we say that this instrument can measure only above 0.38 Newton, or how it is? Like?
Yeah. So that is what it is. So if you want to measure some force at an interval of 0.5 Newton or 0.4 Newton, then this instrument will work fine.
Okay.
Okay.
So, based on resolution alone, we can't declare.
We can't declare, because the resolution is not the only thing. There are other errors that will crop up when you do measurement. So basically, that is the whole point, that not just the resolution alone will only talk about the zero order uncertainty, but there are other errors also that are there. When you buy certain instrument, if you look at the specification sheet, typically they would mention not only the resolution but also other errors that are associated. If you buy a pressure sensor, if you look at the data sheet, all these different kinds of errors that will be mentioned there. So you really need to calculate the design stage uncertainty to say that, okay, whether this will serve your purpose or not. You cannot just rely on the resolution. That may give a false impression.
Okay, sir.
Okay, so if no further question, then we will meet next week. So yeah, have a good week. Until then. Thank you.
Thank you,
Thank
sir.
you so much.
Thank you, Professor.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.
Thank you.